Good morning, or good afternoon, or good evening, depending on where you are. This is the IFAC Workshop Series on Control Systems and Data Science towards Industry 4.0. We're having the third module that's going to be the presentations and discussions today. And these events are sponsored by the IFAC TC 6.1 Chemical Process Control and co-sponsored by IFAC TC 1.1, 3.1, 5.1, and 8.3. So we get a lot of support, and this is hosted by and co-funded by the City University of Hong Kong, the Hong Kong Institute for Data Science. And I'm the director of the institute. I'm also the dean of the School of Data Science at City University of Hong Kong. Also, I'll be the chair for this module. So I want to welcome everybody to this module 3. I think I want to remind everyone the scope or objective of this workshop series was to promote the importance and prevailing trend of data science, AI, and control systems. In the angles that from different expertise and scholars, that's from all over the world, okay? And it's also the Hong Kong Institute for Data Science mission to promote data science and other related disciplines. I personally have formed a view that I think systems concepts or theory should be one pillar for data science. Let's see what's going to unroll over time. So now this workshop has been conducted online through Zoom. We had hoped that we might be able to do it in a mixed mode, but this opportunity had never happened. So I hope someday we can meet in person. So these are the 3 modules of the workshop series, just to review them. And then the first one was data science and control systems theory. Okay, and the second one happened about almost 2 months ago. It's on focusing on chemical and biological systems. And today we have the module 3, and that's focusing on electrical and computer engineering systems. So this is our brief agenda, and we will wrap up by 10:30 p.m. in Hong Kong time, and also 10:30 a.m. in the East Daylight Saving Time. Now, this is our schedule or the agenda for today. So we have 3 distinguished scholars. We're all experts in systems theory, control, optimization, and related applications. So you can see these are the 3 professors. I will introduce them now with the slides, and then when it's time for them to talk, I will introduce them again. So first one is Professor Li Qiu from the Hong Kong University of Science and Technology. He's in the Electronic and Computer Engineering Department. He's director for several centers in Hong Kong and also China, mainland China. The second speaker will be given by Professor Zhongping Jiang, and he's a professor from New York University in the US. He's going to talk from the New York city there. So he's going to discuss and talk about new development in the small gain and machine learning techniques for autonomous driving. And then the third speaker will be given by Professor Jie Chen. He's chair professor at the City University of Hong Kong. Right now, he's physically in California, so he will show up a little bit later. His topic will be interesting is to revisit PID. Okay, so I think after the 3 talks, we'll have about 30 minutes time to have a panel discussion, and then these 3 speakers will be invited back to participate and answer any questions or any comments you might have. So thank you for all the three speakers, Lee, and then Zhongping, and then Jie, to give us three very different topics. Lee talked about the renaissance or the new phases of face. And then Zhongping talked about this small margin and machine learning. How does that lead to helping us do autonomous driving? And then Jie just finished the talk on maybe a renaissance of PID or some revisiting PID control. Okay, so let's try to use the next 20 minutes or so, since we're a little bit over time, to get questions from the audience. I think what you can do is you can either raise your question. We have just 50 plus people, so you could speak, or you can also type into the chat box. Okay, anybody? So I'll maybe kick off a first question for Lee on this phase of complex matrices. I think it's so Lee, you're tuning in, right?
I can hear you. Yeah.
Okay, good. So it's very eye-opening to see that development of phases for matrices, especially of course it's a complex matrices, and it relates to the frequency domain interpretation of dynamic MIMO dynamic systems. Okay. One thing you didn't talk about is I assume there's going to be a similarity. For example, if you do some transform of one MIMO transfer matrix or something, and then that transform will not change the phase. Things like that. Unitary matrix.
Right. So maybe we look at the matrix, right? If we do congruence transformation to a matrix, we don't change the phase. So of course, a unitary similarity transformation is also a kind of congruence transformation. So of course, it doesn't change the phase.
So that would set the ground for your analysis that you, instead of asking for the upper bound of the phase of a matrix, you ask the upper bound of the lambdas of the matrices, right? Like once you do that transform, you could talk about
and not really though, because all this the transform of course change the eigenvalues, right? So if you have a matrix C, you have a bunch of eigenvalues. Then you do a whatever the congruence transformation, that you get a new matrix. The eigenvalues change.
Well, would there be some similarity? Would there be some similarity transform that doesn't change the eigenvalues?
Right, just like unitary similarity transformation.
Yes. Okay.
Of course, it doesn't change the eigenvalues. So basically, the phase is actually for matrix you have a bunch of phases. Those phases are somewhat related to the eigenvalue phases, but not completely. So basically, it provides some kind of estimation. If you know the phases, of course you can actually do some bounds on the eigenvalue phases, but not exactly. There's no exact kind of connection.
Yeah. Okay. My other question actually tried to connect your talk to Jie's talk about the PID nature. There's a connection there. Of course, they all can be said in the frequency domain, right? But my sort of connection is philosophical. I think you're studying this phase of matrices for the most general case. of course, there's no approximation you're doing. However, in machine learning or data-driven methods, data analytic methods, people always try to do reduction. Okay, if you do principal component analysis, it's a reduction. Therefore, we're not going after the most equivalent or complete representation. We'll ask for a skeleton or something that's the major one. Now, how does that relate to GStalk? I think the PID, the way GI interprets, is actually a reduction method of the full, LTI controller, arbitrary degrees of freedom you could find. Somehow, I see the PID is really doing this reduction as a priori knowledge somehow. Okay, so either side for both of you, either for leak to say, okay, there could be reduced sets of things that's easier to derive and more could be very useful. And for GIA, is there a way to interpret PID as like a simple basis of a full set of bases?
Okay.
Yeah.
Lee, you want to go ahead?
Yeah, I think you asked quite a few questions. Especially when you talk about how to connect the phases with PID control. I probably need more thinking to answer that question. Maybe G can, have a more ready answer. But in terms of what really the phases tell us, just like what you said, that very often we need to do approximation or matrix. Very often we need to do represent a complicated matrix using some kind of a simple matrix or something like that. When we use this, we use this approximation or kind of a compressed data to represent a arbitrary or complicated matrix. So what are the features you want to preserve? That's a question. In many cases, they say, okay, I just want to preserve, say for example, the rank, or we want to preserve or want to make the distance, the approximation error to be small, things like that. But are those features that these are really the most important features you want to preserve? Maybe phases give you another perspective. Maybe the phases of a matrix represent a set of other important features, which are important when you want represent data or approximate data or store data. So can you say, okay, I want to find the simple matrix to approximate another matrix so that the phases are approximated properly. Things like that. You can actually raise these kind of questions and try to give answer. In many situations, actually, the features or the information represented by the phases is actually important. You might want to represent well with small error, something like that. So indeed, I just feel that with the new definition of phases of a matrix, you basically add a complementary part to matrix analysis.
Yeah.
to the in singular value analysis. So
yeah, thank you. And Jay, any comments?
Yeah, I think Joe, you're absolutely right. I think at a high level and philosophically or heuristically, what PID control attempts to do is actually to just cope with reduced dynamical system, right? And to counter the negative effect, negative impact of unmodeled dynamics. So if you think, if you take just one step back and think of what PID control does in terms of design and tuning, you basically just implement it. You don't care about what the actual system you are dealing with, right? And then you tune the parameters. So which means that the physical, when it comes down to implementation, the physical system is not that simple. It's not the first order, it's not second order. It could be a lot more sophisticated, more difficult to deal with. But essentially, what you can see, whether you you have stable dynamics, you use Ziegler-Nicholas tuning rule. It's all based on first order, right? The first rule is based on the first order physical process, and the second rule based on second order physical system. So you always just deal with first and second order. Implication is that that you have ignored dynamics, the unmodeled dynamics there, but still it performs well. Now, Lee mentions what to preserve, for example, right? In your face. And in this case, because inherently you are dealing with a reduced model. So what to preserve? It turns out, in my reckoning, PID control is actually quite insensitive to what to preserve. Yeah. So it has it means that it has a really good property in robustness, and that's why that probably explains why it would perform well, because it's insensitive to what you preserve, what you throw out, and so in a way, in terms of it's a possible connection, or even just far cries to things like all this, the processing of the big data and so on. I think it may be worth thinking the PID control, or let's say first in terms of modeling, you use like a first and second order system as a building block, and this is essentially what has been done in mechanical systems, right? You have all this lightly damped systems. So you always use combinations of second order systems, right? And now PID control may also be used as a basic building block, like a spline in approximation, So you can use combinations of PID controllers tuned to specific, for example, frequency range and so on. Just like when you do approximation, you use splines to fit the data in the curve, all right? So use PID as a building block, as a basic module, like that, okay?
Yep, okay, thank you. So I guess we take one question from the audience. That's from Shambhu Prasad. He's asking the one for, I think for Lee, is how to evaluate a phase error norm. Is there something like a H infinity norm, or yes or no?
Phase error norm. Let me try to understand the question.
Yeah.
Indeed, you know, a phase is itself is not a norm, right? It's just you know, you give a matrix. I can give you a set of phases. You may, you know, also look at the norm of the phases, basically, because this is a vector. You have a bunch of numbers, right? And then you can look at the size of this vector. That's actually we look at this. This is we call the gauge, the phase gauge function, or say you simply can call the phase norm, but it's not a norm on the matrix. It's a phase on. It's a norm on the phases. What does it measure? Okay, it measures how far this matrix is from a positive definite matrix.
Sure. Yeah.
We know that a positive definite matrix has all the phases zero. You know, has all zero phases. So that's a you know, that's from phase point of view, that's kind of best matrix. Huh? A set of base matrices. So you sometimes you want to see how far your matrix is from these so-called best matrices. That might be useful actually. So of course, you know, when you say the connection with H infinity norm, then this goes to the system. When you have a system, H infinity norm, of course, gives you know, somehow measures the gain, right? You know, that gives the gain of the system. So that's why, you know, when you say in small gain theorem, we use H infinity norm. In H infinity design, you know, we will try to minimize the gain of system. Phase is a complementary concept. Just like imagine, in the old days we have we have a single input, single output system. Then the gain is just like the magnitude plot of the body plot, and the phase is given by the phase plot of the body plot. So basically, they are well defined. Now the thing is that in the matrix case, in the multivariable system case, MIMO system case, all right, we you know, for many years people are trying to obtain this phase concept. Actually, G also worked on this 20 years ago to try to come up with kind of phase concept for multivariable system. Different people have tried. Actually, you know, if you really look at it, look into literature.
Yeah.
But I think precise definition was lacking.
Yeah,
that's a precise definition.
That's I think the eye-opening part. So let me ask a question for Zhongting, who talked about this really the autonomous driving as a control and a machine learning problem. I think for the three talks, the control sort of definition is always basically the regulatory control or set point control. Okay, so it's driving the error to as small as possible. However, for human driving and many things we perform, we don't aim for minimum errors. We aim for controlling within a band, okay, within a region, and that's good enough. Driving in between the lane, you know, the two lane lines, okay. So that's actually what we do. We're not going to follow one line, but we have two lines to bond us as a range. That's more typically human intelligence or what humans do well, and that's good enough. And I can say in process control and model predictive applications, most of the controlled variables are range controlled. They actually have a more controlled variables than manipulated variables because their controlled variables are mostly set as a range. Therefore, my question for you, Zhongqing, is how would you adapt to this range type of control scheme?
Okay, Joe, good question. So, okay, now I have not presented all the results on learning-based control, okay, now at the MIU. So I think, okay, to begin with, okay, now, so the reason why we want to achieve asymptotic convergence results or asymptotic stability results for the closed system is because that the asymptotic stable system, linear or nonlinear, is inherently robust to some classes of disturbances. So that's why, so due to this inherent robustness guarantee from asymptotic stability for the closed system, so that's why we develop result for it. That's number one. So we can achieve that for only for linear model. So in the nonlinear model case, I don't think that if you apply the best possible machine learning or AI technique together with the best possible control theoretic result, you are able to achieve so-called asymptotic stability. That's rare. I'll tell you why in a minute. So we have to live with so-called range control, but that's something with that have been studied by mathematicians long time ago. So they call it predict stability. So basically, system will not converge to the set point or equilibrium point, but they will stay in a range neighborhood of the equilibrium point. That's called predict stability. I think our framework can be generalized easy to that one, which has been done by a lot of people, including ourselves. So for autonomous driving, eventually vehicle will stay around the center of the lane, not exactly. So so I'll not tell you why we cannot achieve asymptotically converging results for nonlinear model, because when you borrow the languages from AI machine learning or deep learning, then eventually we have to face this fundamental challenge from the network approximation, all kinds of neural network approximation, to approximate nonlinear dynamics or gradient of the value function. So then eventually approximation can never be precise unless you're talking about linear system or polynomial type system. So you have to tolerate this so-called approximation error. So approximation error in the open loop will be propagated into the closed loop system analysis. So then in reality, we will only achieve asymptotic convergence. So a practical convergence, which means as you said, the vehicle will stay in a range of the center lane, for example, for autonomous driving. But we want to prove that this approach still does much better job than manual driving. So we showed that in the slides, so because humans, control is also, I'm pretty sure it's a learning-based controller using language from neuroscience. Human also learn from data. So I think now maybe we can combine both, human control as logical control. Then we eventually with advanced machine learning, we can also help human to make bad decisions. Because humans sometimes do not make bad decisions in unexpected environment. So then when you use machine learning technique, I think we can contribute to the autonomous driving.
Thank you. Yeah, I'll make one comment and then another follow-up question. The comment is, I have reported the industrial MPC model predictive control like 20 years ago. That sort of just revealed how industry was doing successfully the model predictive control. I think the MPC in industry is still going forward somehow parallel or unobserved by the academia. Still, after my paper, that's like 20 years ago, what's going on now is still unobserved. I'm not saying they're unobservable, but somehow it's still parallel to the academic development. I say this as a comment because I don't expect their direct answers. So right now, the industrial MPC, they have done this adaptive control and model identification and control together simultaneously because they allow the errors to happen in the control objective. So there is a range in which they can perturb the process as long as the range is maintained. They actually do that to figure out dynamics that are pretty identified in real time. Okay, they don't have to do identification test by stopping everything. So then anyway, this is my comment. My question again for Zhongping is you're talking about autonomous driving, so we can sort of step back from the mathematics. Now you also talk about this mixed mode or hybrid, right? When the human in the loop. The question is who dominates? Who is, you know, if there is a conflict between the human driving and the algorithm, who should be overriding whom?
Very, very good question, actually. Now, so I've been working with the transportation people, you know, at the NYU and other places, you know, at DOT. So I think, you know, I mean, there's no consensus now. I think we tend to believe, okay, you know, so that you know, autonomous vehicles should give rise to human drivers, unless, you know, you give an incentive to human driver so that they're going to give rise to the autonomous vehicles. I think if there's no consensus, then eventually autonomous vehicles should give rise to, you know, human operated vehicles. So that's we are working on that topic. We don't have a definite answer to you. Yes.
There's definitely ethical or legal issues there.
Yeah, of course, a lot of it. So insurance company are working on that too, you know. So who's reliable for crash in case of, you know, so vehicle collide each other. You know.
All right.
But okay, I want to make comments to Jay's presentation. They mentioned, okay, towards the end of his talk, whether PID or any traditional control, you know, law will disappear. So I believe it won't go away. So even though we mention AI or machine learning, these big, you know, buzzwords, but I think the fundamentally they have to learn from control people. So control people just tell you, you know, sometimes give them necessary sufficient conditions. You want to solve a certain, you know, optimal control problem or optimization problem. So this is the control you have to use because condition necessary sufficient. I think for me, okay, you know, I use whatever control you use in the model-based control literature. Then I say using machine learning, I don't have to manually tune control offline. So I let the data figure out what type of control gains should be assigned to control, but structure control I will stay. So whether PID or LQR or non-control state or MPC, I just tell people, you know, how to adapt the parameters based on data, based on problem application. I don't give up a control structure.
Yeah, I agree. I think no matter what, just like AI, machine learning, or MPC, there's a lot of understanding that is still required. For example, I was mentioning we're trying to develop a version of explainable PID. Now, what about MPC? I think it needs to go beyond the level of he said, she said, yeah. So it should be explainable, and apparently the AI community has been calling very loud that you know, the AI machine learning need to be explainable. Actually, I'm having a student working in this area. We try to understand and try to use analysis to come up with explanations why for certain classes of problems the reinforcement learning will perform well, and why in other circumstances it just would fail, things like that. Yeah.
Mm-hmm. Yeah, good point. I think the explainable AI or interpretable AI is now it's a hot area for machine learning, and that's also explainable, by the way, because when they apply AI to real systems, that tends to fail, and they want to understand why they fail. Now, for more well-controlled problems like image recognition within a finite set of images. Of course, any database is finite, okay, for images, and then they do well. And so it doesn't mean they can translate to this control problems, let's say, of real world systems. So I think that's an important direction, and that will make perhaps control theorists or control engineers play a bigger role in this reinforcement learning and machine learning. So on the other hand, I would also like to offer the other side of the message, which is we should not wait until everything is explainable to use it, or everything is theoretically explainable to use it. And I think the James Watt's steam engine is the best example to explain why. Because when James put the governor on the steam engine, he could make it work for only a very narrow region. It's a proportional control, as Jia mentioned. Okay, and beyond that region, it'll basically explode. Okay, it'll oscillate, and then to the point then you have to shut it down. And for blacks, the feedback controller, there's a similar thing, feedback circuits, similar things. So for the steam engine, it was James Watt put it together in 1776, and then it's not until that 1868 or so, about 100 years later, James Maxwell, find the theory to prove when that can be stable. It's the almost like eigenvalue problem, okay, or this. So therefore, for that 100 years, if we wait until we understand it, that 100 is the industrial revolution would have to be delayed by 100 years. Okay, so again, for this AI run of machine learning, I know there's a very hot topic. There's a lot on the table. And I'm trying to help industry, or at least industry that I know about, to develop a healthy path to move forward. Do not take too much of a hype. Also, keep some hope. That's what I've been doing. Okay. So
yeah, sure. Yeah. As Chairman Mao also said, arts come from life, right? So, yeah, theoretical research is, to me, comes from two sources. One's the innate thinking, the curiosity, and the other, I think, by large percentage is driven by the real world.
Okay, good.
Certainly.
Yeah, I think, what do we do? Like in the research, we're trying to actually develop ways to explain the world. A lot of situations. I think the small gain theorem is a way to explain, why the feedback system is going to be stable in such a situation. Probably some of those systems might have been there for many years, right? They're running well, so we come up with a theorem to explain it. I do feel the small phase theorem will serve a similar purpose. I do have, maybe I'm subjective because I have been working on this phase stuff for a few years now. I do feel that the small phase idea can probably explain more situations.
Yeah.
Well, you do have a feedback mechanism. The gain is not necessarily small, but because of the phase, the phase matches or say phase, you have this phase condition satisfied.
Yeah, Lee, definitely. I think I will be interested talking to you more about this. I see many possibilities of applying to the industrial problems. For example, in process control, people actually are interested in low frequency problems. Okay, running things in low frequency. That's the nature of the entire industry. It's not like flying airplanes. You don't operate planes like flying airplanes or jet fighters. So there are different focuses. I'm sure your scheme can focus on low frequency side and make things simpler. Okay, so let's in light of time, I would like to say,
Joe,
yeah.
can I just jump in for a quick
sure,
comment?
just 1 minute.
Yeah, I think Lee made a good point, especially to the students and younger people. And the way I see it, for example, the way I see small game theory, this is a display of natural law in terms of a conservation. Yeah, the two games within the feedback loop, the gain of the plan and the controller multiplied together should be less than 1, right? So this is sort of similar like the uncertainty principle. You have a fundamental, bound there. You increase one, and the other must be reduced.
Sure, it's like the first law of thermodynamics, right? You cannot generate energy, right? So that's true. It should be more universal than just in the control domain. Very good. So I hope we in the future have a dialogue with really the machine learning people and think on this philosophical side, because I'm sure both sides can help each other by exploring what the other side think and looking for and or have thought about. Okay, so I would say that I have also a task to conclude this module and also conclude the entire series. So first, just time is a little bit late for people from China or Hong Kong. So I'll say very quickly, thank you very much. Thank you for Lee, for Zhongping, and for Jia to give this very nice talks, very inspiring, and also new results. I like new results, and of course you have pushed the forefront in all 3 different things. That's definitely different from what I've known. Okay, so I'm sure the audience have this similar conclusion as I have. Okay, thank you much. So to conclude this entire IFAC workshop series on this systems and data science, I will share with you a few slides. I know it's a little bit late for people in Asia, so this is what I have. Let's see, I can move forward. So we had the first module about 4 months ago, and that was on general control systems and data science towards Industry 4.0. Okay, so we had Jia as the chair, and then 3 speakers, including myself, Professor Orf Feddersen, and Dr. Hong Zhao from AspenTech. It was very important to include the industrial people in our workshop, and it was well attended as well. And then the second module happened about 2 months ago, and Professor Li Qiu was the chair, and we had 3 very well-known professors from the chemical systems domain, and it's Professor Richard Brass from MIT, Professor Furong Gao from the Hong Kong UST, and Professor J. Li from KAIST in Korea. And it was also very well attended. We had a lot of discussions. And today we have this 3rd module. I already have this organized summary. So you have seen it, and I don't have to give you much detail. It was really 3 very nice topics presented by 3 very good researchers and speakers. We have gained a lot of insight from these talks and the discussions that follow. Okay, now last but not least, I would like to acknowledge the people who have made this workshop series possible. Here are the organizers. I be the National Organization Committee Chair, and Professor Furong Gao, the co-chair of NOC, and also Professor Rolf Peterson, who is the chair of the IPC. And he is also the chair of the IFAC TC 6.1, who is the main sponsor of this workshop series. And this is the list of IPC members. I want to thank them for helping and contributing to this series. Okay, and last but not least, again, I want to acknowledge the staff members from the Institute, the Hong Kong Institute for Data Science, to support this series of events. That's Mark Lee, Sandy Mack, Joanne Chen, and Loli Lee, and also other staff who actually supported the IT. I did not put their names here. Okay. With that, I would say I would like to get any feedback you have or suggestions you might have, and say for something along these topics to say do things in the future. Either have a more formalized workshop series over the years, or do something more formally in terms of printed material. So we have all these talks that's recorded and recorded by Zoom. Okay, and also we have the slides, and these speakers have published a lot in their areas. And so you're very welcome to interact or inquire about additional things from them. Okay. And thank you, everybody. And I also have taken some video or the screenshots over these modules. Now this is really as the final thing. You can see what happened in the last 4 months. Okay. And the module 2 here with a different set of speakers, and you can see Richard and his slides. Strange sort of moments being captured, and this is from Furongao speaking, and he summarized the things very nicely. And then this is from Jelly about optimal control and reinforcement learning, MPC. And there was an audience responses from Jiebao interacting during the panel discussion. And this was from today. So if you have been here, you'll find yourself, okay, started with Lee and nice mentioning about Euler and other people. And this, I like this chart as well. Interesting history. And then the small game talk by Zhangping. You didn't know I was doing things in real time as you speak. This is I'm implementing myself as a machine learning system. Okay, so you have the nice demonstrations of autonomous driving, and this is what Jay talked about, PID and all the things that's important. I like this picture. It's pneumatic, and why we do this. I also like the service that's been done by this the committees. Okay, and that's for you. Okay, everybody who didn't turn on their videos, but you captured here. Bye bye.